Okay, so this talk's by Quanlong Wang, proof of completeness for ZX calculus via normal form based on elementary matrices.
Okay, thank
Take it
you.
away.
So today I will talk about the proof of completeness for ZX calculus via normal form based on elementary matrices. And this talk is based on these two archive papers. So basically, I think I will focus on the ZX calculus over complex numbers, and but at the end I will mention the ring case because they are very similar. So as we know that ZX calculus can be represented by its generators and loops. So first, the generators. In this case, I use the square green box and the identity and the Harman box, swap, cap, triangle, and inverse triangle. And so in the complex number cases, all of these generators can be actually can be represented by the usual circle green and red spiders. And I didn't show them here, but I just mentioned it. And then actually the usual circle spider like this one is a special case where for the green square box the parameter is e to I alpha, and the usual phase-free spider is just the square box with a parameter 1. And this empty square is this square just means empty, and this triangle just down triangle just means a transpose of this up triangle, and this similar inverse triangle. And here, so we don't define the general green red spider. So here it's not actually red; it's as a pink. But anyway, let me just say red. The usual we don't define the general red spider. That means spider with parameters with over any complex real numbers. Here just 0 and pi, and it's defined by the green spider conjugated by the Harman gates, and with the is a half. Actually, this scalar is a half. It's a trace of minus a half. So it's half with this scalar. And so what does this diagram mean? The semantics is like this. So you can see the green spider. The green square spider is just so here you can see it's quite similar to the form of the general circle spider, but here it's just A, the complex number A. For the for the phase-free red spider is actually, as we can see, is just all the coefficients. If you just represent the red spider in the standard basis, then all the coefficient is just 1. So the Harman is just the integer part. There's no scalar 1 over root of 2. And the others, this kind of are the typical interpretation. This triangle is just the elementary matrices. It's the second row plus to the first row, and this is the inverse. And this actually is just because for now, this red pi dot is just strictly the cat 1. So pi A is just the A, interpretation just A, strictly. And the loops are all of the loops are here except for the structure of the category, like the snake loop. But you can see here it's not quite so The first one is just fusion rule, right? And this is just the usual S2, this is the usual S3. And this empty rule means any A can, green box A can be, how to say, uniform, normalized by the red dot. So still you can see here, this red dot is strictly the cat 0. And here, this 0 and pi can be, red 0 and pi can be copied by the green spider. And the biological rule, you see there's now, because it's normalized, so now there's no scalar here in the biological and the copy rule, there's no scalar. And this break means the triangle can be broken. So here you can see there's no loop. So here that means that the standard basis, cat 0 and cat 1, they are operated by the triangle. Then you got another non-orthonormal basis. And here you can see this actual triangle can operate on the square box A. You can see you just got the face plus 1, so it's a successor from A to A minus plus 1. So this inverse loop. And this is means the 0, green 0 is just the red dot. And here I call it Euler, but actually is a decomposition of the Hadamard. The Hadamard with, you can see just the triangle and the green box. And the last 3 ones basically means this big triangle, they are symmetric and associative, and can copy any face. You can see one face become 2 faces. Okay, so that's all the loops. And if you can, I think you can prove, or you can just assume that the upside down flipped version can still hold. And also, since we have the Hadamard, and then if tau is just 0 or pi, then there is a color changing rule between the green spider and the red spider, but with the scalar here. So the two. So now, because of the Hadamard has no scalar, so when you use Hadamard, the color changing rule, then the scalar from different directions, the scalar are different. And then, because we just consider the 0 and pi faces for red spider, but now they also have a fusion rule. Be careful here, just the one connected line. So in other cases, they're just as the usual red spider fusion rule. Now, so let's talk about the elementary matrices in ZX. Here I just talk about two special two types. So one is a low addition, and especially from the bottom row, to if it times aj to the other row, like the jth row, from I count from R0, the 0 row, then the corresponding diagram is this one. So basically you connect to, with triangle, you connect to each wire, but here for its output, you connect with some wires. Let's say it's J1 to JS, you connect to J1 to JS, at least one of them. And then, so how to decide the J? So which row you make the low addition to? So here the formula is J is equal to 2 to the n minus 1 minus this sum. And also there is a low multiplication. Low multiplication means you just do the multiplication on the last row. So here I just multiply a to n minus 1. So it's an arbitrary complex number, including 0. So okay, so now we have these two. This can be verified. You can have a look at my paper. So so now we have these two representations of the low addition and the low multiplication. So what can we do by these two? representations. So actually, we can construct a normal form for any vector. Let's say there are 2 to m dimensions, complex vectors. They can be uniquely represented by this this normal form. Here, the top one, there are m wires, and there are, and on the top there are all pi or red pi, and then there are all the in the middle there are all possible this low addition, all possible low addition. That means the connection can be just one wire, just connect to one wire with red nodes. Can be any of them, and can be connected to 2 wire, or can be connected to all the m wires. So there are totally 2 to m minus 1 low additions here, and at the bottom there is the low multiplication. So just this one. So how do we get this normal form basically? So the idea is very simple, because for now the red pi is just strictly ket 1. So the tensor product is just all 0, just but the last element is 1. And from this vector, if we do the low addition, you can see from bottom to the first to the zeros and the ones, and until these 2 to m minus 2s. And then you get, if you do this, you can get all of these elements. And then you do the last multiplication on the final row, then you get the whole vector. So that's the idea, because we have the representation. So that's the idea how you get the normal form. And in the paper, we proved that all this is unique, because all of them, they can, these low additions can commute. And so because of the map state duality, so we have the universality of the calculus over C, because we have the normal form, right? And actually, for completeness, so the idea is if the completeness means for any 2 diagrams, ZX diagram D1 and D2, if their corresponding matrices are the same, and then D1 equal to D2, these 2 diagrams are equal, can be derived from the ZX rules. So, so to prove this completeness, that's the goal of this talk. We use the map state duality. So because of the map state duality, so we can turn each map into a state diagram. Right? That means each diagram, if it represents a map, then we can use bending and to turn it into state diagram. State diagram means there is no, my diagram is all from top to bottom. So there is state diagram means here there is no input. Okay, so now we just focus on the state diagram. So how do we prove the completeness with such a normal form? So so at the beginning we assume that the D1 and the D2, they has the same matrices, which means if we can rewrite each all of the these 2 diagrams, D1 and D2, we can, for this we will assume they are state diagram. If we can rewrite them into normal form, and then D1 and D2 must have so they must have the same normal form, right? Because they have the same matrix. So if we write them into normal form, they must have the same normal form. And so we can first, so then we have a strategy. So we can first rewrite the D1, the diagram D1 into D2 by first rewriting D1 into its normal form. And we will show later how to rewrite it. And then we invert the rewriting from D2 to its normal form. We can also do D2 to its normal form, but we can invert it. Then we got a rewriting strategy from D1 to D2. So that means if we can do assume from this D1 matrix is equal to D2's matrix, then we can rewrite from D1 to D2. Okay, so that's the idea. So now let's have a look at a general state diagram. What does it look like? So basically, it looks like this. There are finite. Basically can be separated with finite box. So each box is has some parallel diagram. On the first, on the top one is a state diagram. So it must be composed because the state diagram is I just separate them in different levels. So the first level must be composed of a cap or a green node, right? And for the others, they are just generators. They can be seen as generators. They composed in parallel. There's no sequential composition in each level. So you can decompose the whole state diagram in this form. And then you can see that, let's look at just two levels. The first is the state diagram and composed with a parallel of generators. And then you can see that if we can bend for this parallel generators, we can bend in the wires, and then we got this one. And if we can turn, so you can see if we can turn this one into a normal form. This is a cap and a cap or the green node, which are generators. And here is also the generators, which is bended into a state diagram. So if we can bend, we can either rewrite generators which is already a state diagram, or generators which is bended into a state diagram. If we can turn them into a normal form, and also if we can turn the tensor products of two normal forms into a normal form, and also if we can turn that giving a normal form, if we can this giving normal form, this is a self trace, right? This is a self trace. We can do self trace once. If we do the self trace with self plugging, we still got the normal form, and then we can say that for each diagram, right? For each state diagram, we can turn them into a normal form. So basically, to summarize, to prove the completeness, we need to prove the following statements. The first means the tensor product of two normal forms can be rewritten into a normal form. And the second is a self-plugging on a normal form can be rewritten into a normal form. And the third is all the generators which is bended in the state diagrams or already being state diagrams can be rewritten into normal form. And so because there are so many things, so many details for this proofs. So I will focus on the first, which is most difficult one, how to rewrite the tensor products of two normal forms into a single normal form. So first, for the trivial case, so actually I didn't mention that if this is just scalars, then its normal form is is pi and plus a. So if its value is a, then it's a. So it's of this form. The normal form for scalar is this form. So the tensor products you can see of two scalar normal form is easily can be rewritten into another scalar normal form. So now we just focus on the non-trivial case, which means it's not scalar. So here you can see that we're given two normal forms. One is from A0, representing the vector from A0 to A2 m minus 1. and the other is B0 from B0 to B2n minus 1. So all of them, all of these are complex numbers. So we want to show that, oh, these two tensor products can be, their normal form, they can be rewritten into a normal form. So how to do that? To prove this, we need to to order them to order them in a good way. So here, by naturality, you can move them freely. So the order is from A0, A1 to A2m minus 2. And then B0, B1, and the B2n, the last B. And then at the bottom is the A2m minus 1. Here I just use the box, green box. I didn't put on these triangles and nodes for simplicity. Okay, so I first put them in this way, and then okay, I use for simplicity. I also use some denotation. So here, this is actually the general AND gate. So I just use the AND box. So here, if there is a green box with some triangle as input and also some output, and I use this symbol. So they have a relation like this, but it's not important. Okay, so the one key thing is, if we give a row addition, give a row addition in diagrams with m inputs, you can see, and there on the left, if there are n whiles identities, and this is a special tensor product, right? This special tensor product. And actually, if you look at the details is shown in my paper. So actually, there is a beautiful thing, that is this one. This tensor products can be rewritten into this way. So this is very symmetrical way. So on the rightmost m whiles, they are just all repeat. You can see you repeat this part. You repeat this part. Repeat this part, and the connection is to J1, JS. Here is also J1, JS. The connection, they're all the same, but just on the left n most whiles, and they are different because they all this A connect to all of them, and that's a red pi pair. I call red pi pair, and they can connect it. They can have how to say. And you can see all the possible cases, that maybe connect to just the connect area n wires, but just some of them has the red pi pair. So maybe there is zero, no red pi pair, but so there's 0, 1 until n. So they are all possible. If you sorry, here you cannot see it clear, but if you plus all the cases, you can see that there are 2 to n. There are 2 to n. There are 2 to n. This elementary matrices, low addition plus a pair of pi, plus some pairs of pi. And symmetrically, if the n is on the right, is similarly. And also for the AND gate, for the row multiplication is similar. On the right, if this is on the right, is also similar. So that's the one key thing, that you want to turn the tensor products into the normal form. But as you can see clear that for now, if we look at the tensor product of these two normal form. So let's go back to here. Sorry. So here, because I have now I have a giving order. So the first giving order. So and then I apply the just I show the tensor products. So here you can see wires. You can see wires. So this is this one can tensor with these wires. Then you got a family. You got a family. You can see you got a family of I call them a family of the AIs, right? So here, so AI just means, oh, I just tensor this, use the tensor products, tensor the low addition or low multiplication with the wires, with the identities. Then you got a family of them, 2 to the m or 2 to n. You got a family of them. And then, because for now, because for simplicity, I just use brackets, and that means a family of them, And then, so now they are all, actually they are all connected, right? After the tensor product, they're all connected. So now, so how do I do them? I do them step by step, of course. So first the diagram. So in any AI family or any BJ family, they are all in each family they are commutative to each other. And now for the because we want to get the tensor product, that means we want to get the here like coefficient to be a product, So so first you can see here the last one, this one here, you can see last one. There is all of them, the 2 to m to the n. There are 2 to n of the element. There are 2 to n elements in this family. So, but all of them, all of them has the red pi pairs, except that just one has no red pi pair, and that one can be put because they are commutative. They can be put at the bottom here, bottom. And then here in this family, you also have because they are all low multiplication, so they can. That is one has no red pi pair, so they can also move the move to the bottom of this family, and also because commutative with elements of this family, and so use this one. Sorry. So use this formula. If they are the same, they connect to the same wires, then the parameters just confused. They got to the product and multiplication of A and B. So that means, oh, then you get the at the bottom you get the 2 to m minus 1 times 2 b to n minus 1. You got this form at the bottom of this diagram, and then you then for the top here, for the AI family, there are 2 to n of them, but any one has all of them has this red pi pairs, but any one has no red pi pair. But you can see from here, from this diagram, so it's proved in the paper. So here, once there is on the top of the, which is just below this the first level pi, if there is any red pi pair, then you can see that it can be then this becomes 0 and it can be copied, and then all this can be eliminated, and then you still got the O pi. So what is left in the A0 family is just the low multiplication with no red pi pair, with no this red pi pair. Okay, so now we call this one just A0, big A0. So now, and step by step for the we consider the B0 family, which is for the A family and the B family. For the first family is the B0 family. for the first for the B0 family, there are 2 to n minus 1 diagrams with red pi pairs. But any one of them, you can see, given that A0, given this A0 has some connections to these wires to J1 and J on the JS, but you can pick just one and any one of them. They you can see the red pi pairs of this B0 family has the same distribution of the A0 family, which you can see, the distribution means that for A is the red, the A connect to the wires with the red nodes, not the triangle, with the red nodes. So you can see as any one of the element in this B0 family has the same red pi, the location, right? The location of the red pi pairs are the same as the zero red nodes, which is connected with this A. So it was all of them are J1 and JS. So this one I just moved. It can commute with other diagrams. So it just move through. Move to the top and undo this A0. I didn't put A because it's a general diagram. And then, that is a property lemma that once in this case, then you can see this pi, because we don't want at the end we want to a normal form, which means just products. We don't want to have these red pi pairs, so we need to eliminate them. So now you can see, because of this lemma, you can see that once we pick up this element from this B0 family, then you can see, oh, we got a tensor product, we got a product here, but also this red pi diagram is eliminated, and this A is still there. You can see, and also these two diagrams are commute. They can commute, so I can just put them. So I can just put the A0 B0. This one, this A0 B0, this one. Just put them down, push them down, and commute with all the other diagrams. And undo the bottom, which is right above the previous product A 2 to m minus 1 times B to m minus 1. Okay, so that means what we did is we choose one. We have this A0, and which is anyone left in the A0 family, and we choose this B from the B0 family, and we get a product, and this pi red pair is eliminated, and we can do it, and then in the third step we can do it similarly for the other BI. It's not any B0 family, for other BI from B1 to B2 to n minus 2. So we can do the similar things. So then we can get all the we pick up the same pattern, right? The same local place distribution. So we can get all the BI A0 B times BI. We can get all of them and push them down on the bottom. And then we choose the because we have choose all the B0 from the all the BIs from 0 to the n minus 2. But now for the 2 to n minus 1, which is multiplication family, we can use another lemma. That means we still consider because it also has for this B2 to n B2 to n minus 1 family, it also has some red pi pairs, right? So we can choose them. We can choose them. So what we can do is we can choose how to say we can choose the for the B0 B2 to n B2 to n minus 1 which has the same location distribution of the red pi pairs as that of the A0 box. A0 box, and so we can still do the same thing, but use different lemma. We can choose this one and have the same pattern. Here you can see both are J1, JS, and then you can push them commute. They can commute with every other diagram and push them to the top, and then you can see here. Once you push them to the top on this A0, then you can see that on the left, you can see that this red pi pair diagram is eliminated, and also this old one A0 is eliminated. Then you got the products. You got the products, and which is a part of the normal form, of the new normal form. Then that's what we want, and we can push it down to the bottom, and then repeat the previous 4 steps. We can do the same things again and again, but not we begin from the A0 family, but we can take other families like from 1 to 2 to n minus 2. And then if we do this again and again, so then what do we get now? So for now, what remains is the following diagrams. So is a family with Bj, which because all the red pi pairs are eliminated. So J is from 0 to 2 to n minus 1. So but without the red pi pair, so just one element in the family. So and also the 2 to n minus 1 family with red pi. The without red pi diagram has at the beginning has been combined into a product. And also the already produced products is AIBJ. And the first product. So that's what we have now. So we need to also, so what we still need to get the products A to n minus 1 times Bj and eliminate all the non-product diagrams, which has red pi pairs. Okay, so actually we do the similar thing. That means we use the we choose a diagram which is in the family A to m minus 1, but has the same local distribution with the with this bi diagram, which is low addition, and they can commute. It also use some the commutation, and then you can still use the actually use the same. You can use the same lemma, and then you get here you get the red pi pair is eliminated, and this one is also eliminated, and then you get the product. So that's a similar thing. And then you repeat the last step for the all the bi. Then we can eliminate this A to m minus 1 bi and bi, and we get what we want. We get the product A to m minus 1 times bi. So now that what remains is the red pi nodes on top, and all the products, all the other ones are other diagrams are eliminated by those steps, and then you have the products, which is a normal form. So that's the basic idea of the basic steps for how to tend to tensor product of normal forms into one normal form. So it seems kind of complicated, but actually you can, if you look at it clearly, carefully, then you can find that all of them has, you can how to say, you can repeat again and again, then you get finally a normal form. And I don't want to show the I don't want to show details about how a self-plugged normal form can be rewritten into a normal form. And all the generators bended in state diagrams or already being state diagrams can be rewritten into normal form. The details can be found in the paper. And so that means we almost have done everything. And one thing left is that how to rewrite in the scalars into normal form. So giving us actually scalar diagram, so it can be seen as a state diagram, right, on the top, and then you plug with some caps or a red dot, right, from the bottom, right, and the state diagram part has been shown that can be rewritten into a normal form, right, and a normal form plugged with either with caps or with green dot, but if it is plugged with a green dot, then it can be banded. You can bend it so that you can just have the at the bottom you just have the caps, right? You just have the caps, which is the self plugging. So, but we have shown that for the normal form with more than 2 outputs plugged with caps can be reduced to normal form with outputs. And so we just need to show that a normal form with exactly 2 outputs plugged with a cap can be rewritten into a scalar normal form. So this has been shown in the details proof of the theorem. So I don't want to show it here. So basically for now, we have shown that we can turn everything into a normal form, every state diagram into a normal form. So that means we can prove the completeness. And as for the commutative ring is quite similar, but and anything is you need to be careful is first for the generators you need to have some you need to choose the phase-free spider as a generator. Also, you want to have the pi gate, right, as a generator. And then the rules are almost the same, but you need some more because you don't have color change rule. So this red spider fusion, you still want to have it, and you need to add this one. This one is very useful. Harma on the red the copy and can be go through commute through. It can be copied, and then it become a green node. And for this part, for this triangle part, almost the rules are the same as the compressed number cases, but you need to add one additional rule, which is called the AD rule. This one, so it's not too complicated. So basically, they are almost the same, just 2 additional rules. Yes. So another thing. Sorry, another thing you should be careful is that so in the complex number cases, you a lot of because there is inverse for non-zero numbers, so you can always have simple proofs. But in the ring case, you need to for some cases if you use the a property of the inverse of compressed numbers, so you need to prove it again. So that's another thing. Finally, but basically the idea are the same, and you can look at the paper for the details. So that's it. Thank you.
Thank the speaker. I have a naive question.
Yes, please.
When you give the definition of the ZX calculus, you have these identities involving triangles, like and you have like this one gate or this one circuit which is like has 3 nodes and it forms a triangle, and there's like a triangle, like a.
Do you mean this one?
Yeah. So what is the interpretation of?
This interpretation is actually is actually the W state.
Okay.
Mm.
Is there any more questions? I thought the talk was pretty cool. It's nice that there's a preprint out finally.
Hardy, can you show the addition rule again?
In the ring case.
Yeah, the ring case.
You mean here?
Yeah.
Uh-huh.
Is that a W state again?
Yeah.
This state.
Yeah.
All right. Yeah.
Yeah.
I see it.
I just put it in a horizontal way, but. Yeah, you can trace out this input. Yeah, it is equivalent.
I somehow, for some reason, I thought to get the actual addition operator, you needed to put a pi somewhere, that it wasn't exactly the W state. It was like not of the W state.
Yeah, it's up to, but yeah. But here I just how to say actually you can see as the how to say do you remember in Amar's paper there is how to say is a red it's a black dot. Black dot here. So basically this means here there is you plus the black dot. You put a black dot there.
Is it the? Oh, okay. Is it like a 3-legged black dot and then with like a 2-legged black dot on the output?
Yes.
Okay, so it's the one that's actually, yeah, I see it. Otherwise, you wouldn't have this associativity.
Yeah.
So on if it was the actual W state. Yeah, that makes sense.
Harney, how does your normal form compare to the ZW of arbitrary rings normal form?
So it depends on how do you compare it. I mean, so for example, I played like I showed in my talk during the IWQC. So if you for the simple cases, you have just one output. I mean normal form. So if you do it again and again, two output. So we do it again and again. Then for the simplify the normal form again and again, then you got the general Euler decomposition. And when it is unitary, and then you got the exact Euler decomposition. So that's an interesting thing.
I mean more like your normal form is based on you start with like a very simple state, like it's the 1 0 0 0 0, and then you add this thing to each component individually. Yes. While the ZH normal form is based on these matrices that have ones everywhere, and then like a single non-one element, and you do like Schur products of those things.
Sorry, you're asking about the ZH normal form, not the ZW.
No, ZW, but I'm just comparing. Like, I don't know how the ZW works, but like you explained how yours work. I know how the ZH works. I'm just wondering, like, is ZW using like another approach again? Like, is it like built in a different way as well with like different elements?
Different. Yes. I didn't quite play with that ZW normal form. I think it works well. works very well for the entanglement things, but for circuit related things, it's not seems it's not very well.
So if I understand correctly, your normal form is small, whereas there's many zeros in it, right? Like the more zeros you have, the less things you need.
Yeah, very sparse.
Yeah. Well, the ZH normal form is good when you have many ones in your matrix.
Yeah.
Like,
and you can see, as you can see, the between the ZH and ZX in this attribute ZX, there is actually, because of the ones, I think, come from the triangle, right? The ones come from the triangle.
I think the ZW normal form is also a kind of additive thing rather than a multiplicative thing. So if you have a very sparse matrix in the usual sense of sparse, I think you get a sparse ZW diagram.
Yes.
I see Simone is also in the chat. Maybe can you maybe say like how his normal form works with like the transistor type thing? Like when is that efficient? When he's still paying attention to that? Apparently not.
Yes, yeah. So the transistor, as you said, is it's a way to combine the diagrams. So we're doing the addition and the multiplication, but there is also the idea of control states. And here, I'm not sure that there is something equivalent to this, but maybe I missed it.
I think there is something. Actually, yeah, I noticed. Yeah, you used in your paper used the control things. Actually, here the AND gate is mostly used for the control thing.
Okay.
Yeah, control thing is very useful. And yeah, the sampling case is the commutative sampling case is also similar, but you have less generators, and so that you have more rules, but not too much.
I have another question.
Yeah.
What's the relation? Maybe I mean, probably lots of other people know, but what's the relationship between the AND gate and the W state? Because they seem kind of related to each other.
The AND gate and the W.
Like, is there any relation to them? It seems they seem kind of similar in a way.
Wait, but actually, I think they're quite different because for the AND gate, the AND gate is you can see is a kind of a classic computation. But you can see here the double state. You can use a double state to actually plus two phases. So you can see here. It's not bit operations, it's just real addition.
Okay. And I have one more question.
Mm-hmm.
So you have these your equations involve these boxes with equations inside them. Do you know that if you're working over the, say, the ring of integers or something, can you just remove the equations involving boxes and do you just get everything for free? Like because you can represent maybe this is a bad question, but like I'm just wondering if there's for some simple fragment, if there's a way that you can like get a presentation for the ZX calculus over a ring without involving these equations inside boxes, but you can just do it like with no extra equations. Is that possible? Do you know? If my question makes sense.
I didn't really understand your question.
Like for some fragments of the ZX calculus, you don't say for the you don't really need like axiom like these you don't need like these bound variables as in the axioms. So
I mean
like
the
for
phases,
instance,
not the phase.
yeah. For instance, like yeah, that's one example where you like multiply two variables,
Mhm.
but like say in the phase-free ZX calculus, like with no triangle or Hadamard or with no Hadamard boxes, you can like present it just with only equations not involving these variables.
Mhm.
My question is there any like fragment where you don't need variables where all your equations just like make it
Well, if you take a fragment of them, then of course you can have just phase free, right?
But is there like like for the phase-free maybe what is the phase-free algebraic ZX calculus?
So here, that means here, if for the green, all the green box here, the elements are just one. They're just one.
Cole, I think in the phase-free case, you would get Vilmar's calculus for the triangle.
I didn't hear what you said. Sorry, can you
I
repeat?
think in the phase-free case, you would get Renaud Vilmar's calculus with the ZX. He calls it ZX and the ZX triangle, I think, or delta ZX.
The Clifford plus T.
No, it's not Clifford plus T. It's just it's I think it's a green spider, red spider, a pi, a Hadamard, and a triangle.
You mean the real?
It's equivalent to phase-free ZH. That's
ZH.
Yeah.
But for H, you have here you have the -2, right? In the, but you use the Hadamard user generator.
Yeah, but Renaud's version is like it represents the integers, I think, or maybe integers with a square root of 2 or something.
The dyadic rationals. Is that? Okay, that was a kind of a weird question, but I was just a bit interested.
Yeah, the good thing for another good thing for this not a semi-ring is the as I mentioned before is the QD case. You can generalize the triangle into a higher dimension, and then you get the normal form of the QD vector. I have shared the normal form in my QB talk.
Cool. Any more questions, comments? In that case, let's thank the speaker again.
Thank you.